Okay, so now this looks like a mess, but this was kind of like a fun little exercise. I kind of found out later that this motor is not a 4PT, even though it's like the same size as one. Kind of crazy. So it's a 4BD1T. Looks like a 4PT. 35.4 cubic inches. Um, and it has an N normally aspirated dynograph, which is awesome, right? Because then we can go do some cool little VE estimations with this thing. So it's like a cool practice. This is like my before, where stuff's everywhere, and then this is like organized. No, 3,200 RPMs is 78 kilowatts, and at 2,000 RPMs, making 55 kilowatts. Um, while it's making 78 kilowatts, it consumes 245 grams kilowatt hour. At 2,000 RPMs, it consumes 55 or at 55 kilowatts, it consumes 230 grams kilowatt hour. So we're going to come over here where stuff's more organized because I did these top to bottom. So it's 235.4 cubic inches, 3,200 RPM, 78 grams kilowatt hour, or 78 kilowatts hour equals takes 245 grams flywheel. So how to convert this over to the horsepower side of things is we take 245 times 78 to find mass grams and divide that by horsepower, because we're just going back to where this originally where this came from was the mass grams moved and then divided by the horsepower number. Uh, so that gives us it's 19,110 grams divided by 104.6 is 182.69 grams horsepower hour. To convert that to pounds, the conversion number is 453.592, so it's 182.69 divided by 453.592. That gives us 0.402 pounds hour. If we want to go now, we want to convert back to pounds in an hour. It's 0.402 times the horsepower, 104.6. That gives us 42.13 pounds fuel an hour. Divide by 60 gives us 0.702 pounds minute. And then depending on the AFR we want to run, say we want to run 20 to 1 AFR, which is probably realistic. I mean, I have no experience with this engine, right? We're just going to assume 21 AFR. So this is wide open throttle in the dyno, what it's doing. It's an older engine. This is probably fine. And it comes out kind of realistic. So at 20 to 1, that means we need 14 pounds of air. 0.073 pounds per cubic foot is I think 90 degrees or so, 80 degrees. Inlet air temperature, so that comes up to 192.3 CFM. So at 3,200 RPMs to get to 192, the engine would be 88% volumetric efficient. So the AFR goes up, and the VE has to go up, and I would say 88 is pretty freaking good. So 20 to 1 comes out fairly realistic for an engine that revs a little bit better. So it's kind of cool practice. And we'll go do the 2,000 RPM, so peak torque, right? So the engine is the most efficient at peak torque, and it'll show up right here. At 2,000 RPMs, 55 kilowatts hour, it's 230 grams kilowatt hour, so 230 times 55 is mass grams. The mass grams divided by the horsepower gives us 171.6 grams horsepower. So it is more efficient at peak torque than it is at peak horsepower. Peak horsepower, we are 182.69 grams horsepower, and at peak torque, we're at 171.6 grams horsepower. Divide that by 0.453.592. Gives 0.378 brake stick fuel consumption ratio, which again shows that it's more efficient than it is at peak horsepower, as it should be. 0.378 times 73.7, because 55 kilowatts is 73.7 horsepower, gives us 27.88 pounds hour of fuel, divided by 60 is 0.46 pounds minute of fuel, times 20 for the same AFR means we need 9.29 pounds minute of air for this engine at 2,000 RPMs to draw 9.29 pounds minute air at a temperature of 0.073 pounds per cubic foot. It's 127.34 CFM. We get to 127 CFM at 93% volumetric efficiency. There you go. The engine is more efficient volumetric efficiency wise at 2,000, and it's also more efficient with the fuel at 2,000, as it should be. Peak torque is the most efficient part of the engine's operating range, and peak horsepower is essentially the extent at how far out you can rev it before the loss of VE causes horsepower to go back the other way. So, I want you guys make this short little video. It's kind of fun. Did it wrong and had to go redo it because the brake numbers were like super high, and I thought that was really weird. Maybe it was like an NA diesel thing, but no, I just did stuff wrong. So this is going back to it. I said it's a 4BD1T. It's hard to find NA diesel engine uh, flywheel dynographs, but this one had one. I was looking for 4BT NA dynographs and stumbled across this, and pretty close to it. So, guys, enjoy this. Have a good one.